Okay, welcome to part 3. So in part 3, the first thing we'll be looking at is the first law of thermodynamics. So here we have the change in internal energy per mass is equal to the small amount of change in heat, dq, is equal to the work, which is pressure, times dv. So in our scenario, since it is adiabatical and reversible, we won't even be paying attention to dq because that's equal to 0. So that doesn't matter. So we'll only be looking at du is equal to negative p external dv. And the first thing that we are going to do is we are going to replace the pressure, since it is an ideal gas, with RT over V. So doing that, it'll look like this. We'll have du, which again is the change in internal energy, is equal to negative RT over V times dV. And then for an ideal gas, we will replace the du with the constant volume specific heat coefficient, which is going to be CV dt. So our next step will look like this. We will have CV dt, which I just explained what it is, and it will still be, let me clean that up a little bit, sorry. And that's going to be equal to what we have still up here, negative R times T over V dV. All right, now we are just going to shuffle the equations around a little bit. So we're going to bring temperature here over to the other side. So that's going to look like CV dt over T is equal to, R dV over V. So now our next step is to integrate this, and we will integrate it with respect to T1, T2, and the different volumes for V1 and V2. So we'll just go ahead and add our integrations here. We got to make sure we keep the negative, and we'll get V2 and V1. And then on this one, we will have T2 and T1. And then now we will just simply simplify this to be CV natural log of T2 over T1 is equal to, negative R natural log of V2 over V1. And that will do it for the third part of this video. I will see you on the next part, part 4.